One more, and there we go. I won't run short of Paul in the middle of class. Do I got anybody there? Not yet. So, good morning, folks. We're going to do just this, practice with the power grid ideas and review the transformer today. Let me write down my online folks as they join us. Yesterday we did power grid, we did station 4. We did transformer. Hey, I got one already. Good morning, Corey. And today's the 19th. Time is just flying by, people. How about that? Okay, for folks here, let's see then. Yesterday we looked at this device with 2 coils and it changed the what? The device with 2 coils, what did it change? You can look at your drawing from yesterday. What? Exactly. So, we have a device that changes voltage, and if I want the voltage to go down, I use a So what's it called, the device, if I'm changing to make the voltage go down? To go down. Charlotte? You got it. And the opposite, Emily's going to be a? Exactly. So, which one do they use to get the electric current from the power company to you and I, the consumer? Which one do they use there? Michael? Step down current. Transformer? Exactly. And on the way back, of course, they use the other one. Let me check in a couple other folks. Do you need to print off the worksheet? You can just do the answers in your notes if you want, Zach. You don't have to print it off. It's up to you. That's okay. But the answers you could just put in your notes, as long as you can access it, Zach. The worksheet Zach's referring to, I'm going to give all of you in just a moment. But I sent the worksheet to Zach and everybody else on the Google Classroom. So let me write down who else is here. So Zach, I got a Clara today as well. That's good. Hopefully a couple others will join us too. Is this enough? Yeah, it is. Is this enough? This is. Okay, I'm going to hand this out to all of you. It's got a front and a back side. And I punched the wrong side, so we're going to do the back side first. The side that says Transformers. It's not the latest movie, it's physics. This is more or less the review, but I just find it kind of useful. Okay, folks at home, can you find this sheet? It's in the Google Classroom. I sent it to you yesterday. You don't have to print it if you don't want to, but you need to be able to look at it and put the answers down in your notes. Okay, so that's what we're going to work on here first this morning. All right, it says Transformers at the top. It's one file, it's got 2 parts, but it'll be in there. All right, so you go find that. Let's read what we're supposed to do, and I'm going to give you a couple minutes to try and figure it out. I didn't tell you this, but the side that the power is coming from is called the primary coil. Primary means first, right? So it's the first one that the electricity hits. And then it's going out on the other side, that's the secondary coil. So in on the primary, out on the secondary, kind of makes sense. to help you do this, you need to look at this ratio at the top. So 1 to 2, think about what that means. We had a ratio of 1 to 3 and 3 to 1 yesterday. And then see if you can figure what happens to the volts and what happens to the current, the amount of amps. And the bottom one is 3 to 1, similar to what we had yesterday. So what's going to happen to the volts and what's going to happen to the amps? So I'm going to give you a couple minutes to try that. Folks at home as well. So try and get some answers there. And it involves a little math, but you don't need a calculator. The math is pretty easy. So let me give you about maybe 5 minutes to work on it. If you're really unsure, call me over. And I'll check in Ingrid here. Welcome, Ingrid. So Ingrid and the other are going to work on this as well from the Google Classroom. Write down their answers. All right. You're half right and half wrong. And that's half right and half wrong. I know we didn't do part of this. Just think about it, Kiara, for a while. It's a good challenge. How you coming along? That part's right. That part is wrong. You got half right. Think about it. Think about it. Same with you. That top part's right, bottom part's wrong. So go ahead and try the other one down below there, Elias. Right, wrong. I'll let you think about it. You see wrong. You see wrong. That's the amount of transport. Okay. Yes, no. Yes. No. So we'll pick up the second part of going to start the whole one. Come on, yeah. I know it's early in the morning, Michael, but come on. But yeah, that's right. Folks at home, anybody else join us? I got 1, 2, 3, 4. That's a pretty small number. Okay. So be it. Okay. Questions here? We'll see. You got questions at home as well on this? Let me make a spot on the board and folks can help me fill them in. So what do we have on top? We got the step up. Okay, so let's see what the scoop is. For the first one, the primary is on the left, and the secondary is on the right, and we got 1 to 2 ratio, and we got 6 volts, we got 120 amps. Okay, the secondary, how about the voltage? Amelie, what'd you get here for the voltage over on the secondary side? 12 volts is right, and what did you do? Doubled it because it's a 1 to 2 ratio. Okay, good. Now, most of you got the bottom wrong, so I want to give you a little hint as to what's going on. I know you got ideas. Put your hands down for a second. Here's the hint. If I got a primary, can folks see this at home? Well, what's equal is the power. The power coming into that transformer equals the power going out. So what that means is what? So yesterday or the day before, I forget, I gave you an equation for power. Power equals 10 times 10. Good, Sevla, you got it. And it is, Charlotte. All right, thank you. So here's what that means. The I coming in times the V coming in going to equal the I going out and the V going out. I'm going to put in some numbers for our example. And I know a lot of you figured this out because you're quick, okay? But let's do this. So coming in, I got 120 amps, right? Times 6 volts. And going out from Amelie, we got that it's 12 volts. She's right. But then it's got to be what then to even this out, Michael?
120 amps again.
No. The power is the same, but you know what? There's got to be a different current coming out. So 60. Why? Yeah, essentially. So 60. What do I got here? Amps. Let's think about why that is. Just to convince you. What's 6 times 12, somebody? You got that one memorized? Line of 6 times 12? Times tables? Good one to know your 12s. They come in handy. What is it, Laura? 720. You got it. So I got 720. That doesn't write for squat today. Let's use the black one. 720. What's power measured in? Who remembers? What label is power in? Yeah, but it's been a while. Do you remember, Michael?
Watts.
Right. So I got 720 watts. And what about 60 times 12? Yeah. The same, right? It better be the same, right? So what that means is if I got the machine, well, it's not really a machine. If I got the setup, there's no moving parts, then the power coming in equals the power going out. So if the amount of voltage goes up, like we do with Amelie, then the amount of amps has to go down. That's kind of how it works. Okay? All right, with that in mind, will you all take a look at your answer to the second one? See if you can fix that. Same folks at home, try and fix your answer to the second one. Thank you. Thank you. And 72 is right. Thanks. And Watts is right. Thank you. Alessia, you are here. I'll write you down. That is good. I will put that away. Yeah. And I'm going to take an answer here in a second. Don't worry. Thank you, too. But I want to make sure everybody home can see this and see if they got a question. Hey, Avram is here. Oh, that's good. All right, Avram, gotcha. Gotcha, sir. Okay. Okay, to step down. All right, Kiara, you're on. Tell me about this sucker.
It's 360 amps.
Well, let's do the volts first. We're not in it.
4 volts.
4 volts. How'd you get that?
I divided 12 by 3.
So 12, so 3 to 1, 12 divided by 3, so 4 volts coming out the other side. Okay, tell me about how you get the volts, the current, the amps.
I just multiply 120 by 3
Ah,
because when it's set down, the amps go up.
yeah. So I get 300 and, let's think about why we use this. And we're going to sketch this on the board in a moment as well. Could you zoom us in? I got you about as zoomed any more or less and you fall off my desk. So, I know it's not the strongest Wi-Fi in the world. There you go. That's as zoomed as we can get. I'll read it off as well. Okay, so what was given was 12 volts, 120 amps, 3 to 1 ratio, and from PR we got 4 volts and 360 amps. Okay, we're going to write this in a sec, but let's kind of remember from yesterday. Power companies send electricity at what sort of voltage, high or low? They send it from the power plant, Linus? High, good. So I got a high amount of volts. I know it's not this number, but it's just relatively speaking, high volts, low amps. And we talked about various reasons that they do this and change it. Once it gets to the consumer, like Linus said yesterday, it's one reason is safety. We don't want a high voltage, which is right. But the other thing is consumers need a lot of what? Consumers need a lot of what, Malta? A lot of current. And look at this. When the voltage goes down, the current goes up. That's good because you and I need this for our hair dryers, for our washing machines, for our computers, everything we need lots and lots of current for. Other stuff. Yes, exactly. That's right. That's what we did yesterday. Yeah, 300 to 900 windings. Exactly, Alessia. And Alessia, this sheet is from the Google Classroom. I sent it to all of you. So it says transformers. So you can look for that there too. Adam, same thing. That's in your Google Classroom. You don't have to print it, but maybe look at it, huh? Okay. Questions about the two types of transformers and how you do the math. The math's relatively easy. There's no reason it has to be hard numbers. Okie dokie. Then, yeah, Kiara.
I just want to ask, how are the wires connected? Like, how does the electricity flow in the other one?
It creates, they aren't directly connected, are they? Kind of weird. Let's hold it up and think about it. Let's do the step down. Okay, so here's your power source, Kiara, your box with electricity or whatever. So that sends it into this side. And even though it's not directly connected, they're holding on to the same block of steel or iron. And you create in the secondary coil a field, magnetic field. So I do that, and that magnetic field then induces a current in the wires, and the wires then head off with that current. So it's because they're both hanging on to the same chunk of metal that it allows the voltage and current to go lighter, to go further, so to speak. Good question, good question. Anything else about transformers so far? Let's see if folks got any questions about this either. Exactly. Exactly. Electromagnetic field. Good. And Liam is here. Liam, you may want to see the early part of the video because you missed some good stuff. But we're going to move on. Okay, so here we go. Just as a reminder, okay, clear our heads for a second? As a physics teacher, again, I like to tell you rules and laws and all this stuff, but you know what? Even more important for me is that you understand where it is in your lives. Because you use the power and electricity all the time, I feel it's important for all of my students to really have a good understanding what's going on between you and the power plant. And actually in the power plant too, but at least, okay, once the electricity is made, how does it get to us? So I want to just review that and make it really clear. So on one side, can they see this? They can't. I got the power plant. And we're making our power at a high voltage. And low current. Let's make it about, here's our pulse line. Like the one where I used to live at Telto, steam coming out, okay, especially in the wintertime. Okay, so here's our electricity coming out. And before we get to the consumer, you and I, I've got to send the electricity into which sort of transformer? So what kind makes sense? Charlotte? Thank you. Sign and goes plant, and it comes out the other side, and it goes to the consumer. And of course, it's got to make its way back again too. So here it comes on the way back. Now it's going from the consumer, and it's going in the same area. Here comes the electricity back. And between the well, let's go to Linus here. Coming on the way back, before I get to the power plant, I gotta do what here? I gotta use a transfer step up to do this. There it goes, and then comes back to the power plant. And again, physically, these are at the same spot, okay? And again, now that you know about them, when you're traveling around the world, look for areas that are fenced off. I think we talked about this with Michael yesterday, and lots of loops of wire and coils and cones of wire and stuff. And those are the transformers. And obviously there's a lot of high voltage wires and stuff, so they're all fenced off for safety purposes, right? But you're gonna see those transformer stations. That's what it's quite often called. I should tell you that. Transformer station. So we got step up and step down transformers. Okay, to be honest, I'm simplifying it a bit. Before it gets to your house, there's some other transformers as well. But you know what, I'm not gonna put that in the picture. It's okay if you just sort of know what's happening in the middle somewhere, to be really honest. Review from yesterday. IV sent out. So why was it again? Why do power plants send us a high voltage when we can't use it? What's the main reason we send out high voltage? Do you remember, Linus? No, that's over here. I mean, right when they send it. Why do they send it? And to be honest, Linus, the step down would be pretty close to consumers. Most of the time, the electricity flows, it's in the wires that are high voltage for most of the distance. So why do they want this to be high voltage? What was the reason? What was the reason? Hello?
Because if it was high current, it would create too much friction in the wires, and then they would like melt and heat up and use energy.
Or even if they didn't do that, they would lose
Energy.
energy. And when I lose energy, I lose. Exactly. So it's really about money. So high voltage sent out, so less energy lost due to heating wires, and it's due to friction, as Michael said. So it's low current. Low I will say, because that's the letter for current, isn't it? Huge. And over by us, we can say, hey, we need lots of current to run our stuff. How about to run all devices? So I current needed. Huge. Okay. In your home, by the way, what if the current gets too high? What happens? And it doesn't melt your house or anything. But there's like a safety device. You know anything about that, Kiara?
It's called Zico.
Yeah, Zico. What does that do if it gets too high?
Just, I don't know, it's called spring house.
Yeah. Yeah. It's a little switch, and it's on, and if the current gets too high, the little switch does what, Michael?
The fuse switches down to
Yeah.
the hot position.
You got it. You got two things. You got the Zico is really not a fuse per se, but it just switches off. And then, like, before I go and switch it on, it's good if I turn off either the toaster or the washing machine or the electric hairdryer, or, you know what I mean? Sometimes I got too many things on. That's the problem. Okay, but in the old days, there was a fuse that actually burnt. It was a little tiny wire in the fuse and it burned. If you're in a very older apartment, you might have some of those. And then you physically got to put in a new fuse. They're not dangerous. They're behind a little glass porcelain case. But the little tiny wire melts, and then I blew a fuse. That's what we say. I blew a fuse. Does it really blow up? No, it just melts. And then you got to put in a new one. Emily?
When the power goes off, like, in the city or something like that, it is because there's too much coming back to the consumer.
It's a good question. Why does the power go out? Sometimes it's a lot of different reasons. I'll try and give you 2 or 3 on one. Well, actually, maybe you guys could guess. What are some reasons the power might go out in a city or part of a city? What's one thing that could happen? There's probably 2 or 3 that are fairly common. You got one, Michael?
Water damage and the transformer.
Okay, so water damage. We had this at Fukushima when there was a tidal wave. It washed out and really just the lines and stuff were underwater. They didn't work anymore. So you could have a natural disaster like that. I'll say water damage because there's a more probably common one that happens too. What else could happen that could knock out some power or cause a power outage? Give you a hint. This used to happen a lot in Washington, D.C. in the summertime.
It's too hot.
It gets too hot. And what does everybody do at the same time? They turn up their
Current?
Yeah, on one device, if it's hot, on their house or apartment, AC, air conditioning, right? And if everybody in the whole city of DC turns up their air conditioning at the same time, what happens? It uses an awful lot of what? Current. And it can be too much, and then the power grid shuts down. Now, modern day systems, that happens less than it used to. In my childhood, that was not so unusual. Oh, the power went out. Oh, God, it's a hot day. Everybody's got their air conditioning on. And they had to kind of change the grid a little bit. to account for that. So could be overuse or too much use. Could be water damage. What else could happen? Did you have one, Kiara?
Well, I just said the transformer has some sort of damage.
Good. Okay, so transformer could be damaged. Can you imagine something that could damage a transformer? Linus?
I don't know if it's possible or maybe it could work with wires.
Yes, okay. That could happen with maintenance and stuff, but a more simple thing that could happen could be what, Michael?
An earthquake or tremors, it would like take the towers and snap the wires.
That could do that. Could have earthquake damage too. Luckily, fairly unusual in a lot of parts of the world, but in some parts of the world, they do have earthquake problems, and I'll put that on my list too. There's another way I could disrupt power.
With the lightning on it?
There's a really common one. Okay, if I have lightning strikes, if they strike part of a transformer, they may knock out enough so it knocks out all or part of the power grid. Okay, it's not that it melts it totally, but you're adding something. Lightning has a huge amount of both volts and current, and it just overruns whatever the transformer sets up for, and it has to be reset, and maybe some parts replaced. They got to send somebody out there when that happens. That's fairly common. So a transformer gets hit, we say. Good. Let's see if you had any ideas here. Oh, that was Ingrid's idea. Look at, I took the steam away from Ingrid. She said power lines go down due to storms. Exactly. So the power lines can go down as well, coming in and out of the transformer also due to wind or storms. You could have them, or sometimes a tree, right? And suddenly your power's out. If it's going in or out of a transformer, could affect a lot of people. A lot of people. Let's see if you had anyone else. A storm, yes, Zach had it as well. Good, good, good. Oh, and Alessia knew all that stuff about the fuses. Thank you, ma'am. Sorry, I didn't see that earlier. Michael.
In the US, there are like the power lines that are connected to the wooden poles. They'll go out a lot because either like balloons or birds will sit on them. I don't know if the balloon will float up to them or stuff, and then it'll like create a big explosion.
Oh, I don't know about a big explosion, but if I have something sitting on wires for a long time, it's not necessarily good. Yeah, we don't want a lot of stuff sitting on wires for a number of reasons. Yeah.
I have a question. I always do that when I'm in Munich or in Hamburg. In the winter. There's like always those trains with the two wires and the connecting thing.
Right.
And then when it's like snowy or something or ice, and then always it's like little lightning.
Little sparks.
The train drives by. What is that?
Yeah, there's sparks, right? That happens anyway, especially in winter, you notice that.
Yeah, but why is that?
Why is that? I'm guessing you got enough material like snow or whatever on the wires, so the connection is not 100% perfect. So if it connects, here are the wires. If the connection with the metal down here is up, and it keeps going back and forth, I think every time it reconnects, you get a little spark there. So I think it's kind of bumpy and reconnecting. So because of material on the wires, so it's not necessarily always going to go out, as we talked about with Michael, but sometimes you get sort of a flash of sparks.
Yeah, it always looks like a firework.
Yeah, it looks kind of exciting, kind of dangerous looking, but it's not really particularly dangerous. But it looks interesting. Good. Any other questions or comments from folks at home? Oh, I got a good one from Alessia. What about hurricanes? Class 1, 2, 3, 4, 5. Oh man. Okay, so hurricanes are pretty common where my folks used to live in Florida in the U.S. And depending on the severity of the power of the hurricane, like a class 1, class 3, class 5, whatever it is, the winds get a lot worse, right? So you got a number of problems with hurricanes, right? One is like water damage that Michael said. Another biggie with hurricanes is, somebody said it.
The wind.
The wind. Okay, so the wind is tremendous. And of course that causes a lot of trees to come down. So Alessia, with hurricanes, you got a huge number of different problems that can affect your electricity grid. And it's often, as you guys probably read about in the news, sometimes it's out for several days. My own brother bought at one point his own generator to keep his refrigerator going. Because what happens if it's out several days to your kitchen? What happens? Malta? Yeah, the food goes bad, right? Because I'm not refrigerating and it starts to stink and it's terrible. You got to throw it all out. The generator my brother bought was fueled not with electricity, but with diesel fuel. So they burnt the diesel fuel and made electricity, very much like we saw. It had inside of it a coil spinning in a magnetic field. Okay, but diesel fuel instead of coal, like we use here in Berlin to get our electricity. Good comment, Alessia. Any other comments, questions from folks at home about the power system? Whew. We're going to take a look at it officially. So folks at home, now find the other part of the transformer file. Folks, here you can turn to the back side. And the back side is about the power grid. Or here they call it power transmission. Let's read a little bit about this. So, Timothy P., could you read where it says many power companies?
Many power companies provide power to cities that are far from the generator. Consider a city of 100,000 persons who each continually use.
Oh, it's poor English there, sorry.
Who each use 100 watts of power, equivalent to the operation of two 60-watt light bulbs per person. The power constantly consumes 100,000 persons times 20 watts. Person equivalent 12 million watts.
Okay, so, and the M, anybody know what that metric prefix is for a capital M? That's kind of a fun one to know. What's capital M mean? As a metric prefix, it doesn't mean micro, that would be small. It means, do you know what micro?
Megawatts.
Mega, good. Yeah, so exactly, so MW is megawatts. Megawatts. Super. Reminder, we kind of had this earlier, didn't we? We had, oh, let me just, here's some fun we can add here too. We said this is let's just do it up here. Okay, so we had a big voltage times a small current, and on the way back, we got, over here at the consumer, we got a small voltage and a big current. Yeah, that's kind of worth adding, isn't it? To our picture. Big voltage, small current. Why am I doing that? Because we're going to need that here. Look at that. We got the, right down below, we got the P equals IV equation. And we got 12 megawatts or 12 million watts. And I'm going to have you guys do this. It says, number one, what's the current corresponding? Can you write in the numbers? So everybody try and do number one. And even without a calculator, I bet you'll be able to figure it out. So do a little algebra. Solve for the current there. Peachy Keen, let's get it. See, I haven't thought about that. And this would be where would that be? Where would it go? I don't know. What's going for the voltage? We need a lot more what? Makes sense, right? Good, thank you. Thank you, Timothy, those look pretty good. Let me make a spot on the board and Timothy or somebody can help me here. Okay, so number one, million watts, whew, equals I times 120 volts. Okay, so I equals, just put in what you divided. So, Amelie, what goes on top, what goes on the bottom when I solve for I? Oh, Charlotte?
So, and on the bottom, 100.
You got it. So we just divide 120 over. Good. Timothy, what'd you end up with?
Around 100,000.
Amps, right? I gotta think about that always. Okay, so I gotta go take a zero off. So now it's 1.2 million divided by 12. That sounds about right. Others get the same. Does that sound good? Yeah, I think so. Good. Yeah, thanks, Timothy. Now, why am I having you do this? Because I want you to think. Oh, look at that. 120 volts. They don't use that here in Europe. Where do they use that? 120 volts. Linus? In the US. So that's used. So look up above. 120. That's what people's houses, right? Is that a little or a lot of current available there? Little or a lot?
It's not as much compared to Europe. Like,
No. But my question is not about the voltage, it's about the current. Relatively speaking, what kind of number is that? That's all I'm saying.
oh, that's a lot.
That's a lot. Okay. Why is that a lot? Because what? Consumers, Lauren, use a lot. So you may even want to take a little arrow and make a little arrow from there up to the consumer. A little. Okay, a little house here. So I hope that makes sense to you. It's a lot of power available to consumers. Let's go to number 2. Okay, well, sorry, let's read a little bit. I'm sorry, I'm rushing. How about, Kiara, could you read where it says this is an enormous?
This is an enormous current, more than can be carried in typical wires without overheating. More power would be dissipated in the form of heat than would reach the power wasted. Questionably, the important quantity is IV and not I alone. Power companies can the power of long distances at very high voltages, so that the current in the wires is low and meaning of the power line.
Okay, thank you. Let's do number 2 then. So here we go. I need I equals P over V. And this time, we want, and look at that, it's 120,000 volts. That's what's produced. Look up at the top. Where's that in the diagram? Up. When they're sending it, right? 120,000 volts. And folks, what about the top number? Sorry, that's the bottom, the voltage. The top, we're still putting in what for the power? Timothy? You got it. 12 megawatts or 12 million watts. Good. Woo. Okay. Timothy, back to you. What'd you get for that one? I know you crunched it out.
100.
Okay, let's put an arrow up to where that's being used. So that's where in my diagram up at the top. Where's that 100 amps going on? Kiara?
From the power source to the transformer.
Oh, you got it. So look at that. So we're probably got somewhere in here a transformer. Oh, look at it. You can see the little see 240 volts? That's part of a what station? It's not drawn real well, but it's probably what, right?
Transformer station.
That's a transformer station. See the little fencing, and behind it there's boxes. Anyway, it's kind of crappily drawn, but that's a transformer station. Okay, so between the power company, Kiara's right, and the transformer station, that's where they're sending it at a much lower voltage, much lower current, right? So that's the sent current, and this is the received by consumers current. And of course, 100 amps I can send through the wires. I can't send 100,000. That's too much. Yeah, they'd heat the wires too much. Huge. Can you read also underneath there where it says this amount?
This amount of current can be carried in long distance power lines with only small power losses, normally less than 1%. But the corresponding high voltage wires to houses would be very dangerous. So step down transformers are used in the city.
There you go. Okay, so Linus is right there too. The high voltage is also a problem. Okay, so we got 120 volts, but we get a lot of amps available. Super. I'm gonna have you do 3, 4, and 5 on your own because we're gonna run out of time. Do you want to just circle 3, 4, 5 for when I see you again? What, a week and a half? Is that when I see you? I think, right? So, not a big assignment, but, and I'll try and stay online for when I see you next week, so you'll be home. And you can watch me from there and we'll go a little further with some of these ideas. Thanks, everybody. We did real well this week. Thanks, everybody at home. Bye-bye. We'll see you soon. See you next week. Have a good week. Try and finish up at home, could you? Try and do 3, 4, and 5. So try and finish that up for homework. Okay, thanks. Bye, Clara. Bye, Ingrid. Bye, Liam. Bye, Jack.
There,